In this second part, we are going to discuss the mobility of planar mechanisms, and mainly we are going to learn how to calculate mobility of planar mechanisms, to establish the equation that gives mobility, and to mainly after that try to learn how to interpret the value of mobility. If mobility is 1 or 3 or negative, what does that mean? So, as usual, I'm going to start with the learning outcomes, what you are going to be able at the end of this lecture. So, for the learning outcomes, these are what you are going to be able to do by the end of this lecture. So, first, you will be able to define what is the mobility of a mechanism. This is very important. And second one, it is, and the most important one, is to know how to calculate the mobility of a planar mechanism. You are focusing on two-dimensional problems, two-dimensional kinematics. So we will make an extension for 3D mechanisms, but just we will not use it. We'll mostly focus on planar mechanisms. And by the end, also, you will be able to interpret the value of mobility and to predict or to analyze the behavior of the planar mechanisms based on what is the value of the mobility. So now, how we are going to present this. So first, I'm going to recall briefly what's a mechanism. Then mobility is the degree of freedom of the whole mechanism. But to be able to calculate the degree of freedom of the whole mechanism, we need first to understand what is the degree of freedom of one link. So first, we're going to focus on a link or a rigid body, and we are going to present or understand the different degrees of freedom of one link. Then, at that time, we will be able to go and study the mobility of the whole of one whole planar mechanism, or mobility or the degree of freedom of the mechanism. Once the equation of mobility is established, we can see some how useful is that equation, and mainly how we can interpret the value of that we are going to obtain. And before closing the lecture, we need to apply the equation to some examples. So first, let's recall just rapidly what's a mechanism. So as usual, okay, this is what I have already presented. A mechanism is a collection of links. The main parts are links or rigid bodies that are connected together through joints, and the joints or kinematic pairs are of two types: lower or higher pairs. Lower pairs in planar mechanism allow 1 degree of freedom, and higher pairs in planar mechanisms allow 2 degree of freedom. The joints are the contacts between links, and they block some relative degree of freedom and allow some. Now, also in mechanism, I need one to be as the ground. I insist that the grounded link is not necessarily static. It is just considered as a reference for the kinematics of the whole mechanism. Also, a mechanism is transforms motion, so it receives an input in one or more links, not necessarily one link. Sometimes it receives the input in just in 1 degree of freedom of a link, and it delivers an output. The output is a certain motion of one link or a certain motion in 1 degree of freedom of a link. It can be also more outputs. So this is just a recall. Now let's go to the second part, which is to present the degree of freedom of a link. Degree of freedom, sometimes shortly said DOF. Okay, I will try to use always degree of freedom, the whole word. Now, in a link or a rigid body, there is 3 elementary motions. The 2 translation, the horizontal and the vertical translation, and the rotation. There is only one rotation here, the rotation about the out of plane axis. Now, these 3 elementary motions are the only transformations that conserve the shape, that conserve the distance between points, or that conserve the angles. That's why we consider only these types of motion for a link. So this elementary motion, this is the basic motion. In any other motion of the link, for example, I'm just going to show it again. This is a curvilinear translation. A curvilinear translation is a successive combination of the 2 horizontal and vertical translation. So any other motion of the mechanism is a combination of the 3 elementary motions. It is a combination of 2 elementary motion or 3. It is a combination of 2 translation. It is a combination of 1 translation, 1 rotation. It is a combination of the 3 together, the 2 translation and the rotation. So any other motion is a composite motion. It is made of these 3 elementary motions. So also the general motion is a combination of the 2 translation and the rotation. Here again, the body can move in any way. The only condition here, if you focus, the shape is the same. Whatever the motion the body has, the shape is the same. And if I consider 2 points, the distance between the points will be the same. Now, because having only this 3 elementary motions, I will need only a set of 3 parameters to describe the position at any time. So if I want to know the position of the link or the rigid body in 2D in plane at any time, I just need 3 parameters, a set of 3 parameters. Now, one possible set of these parameters is to consider the coordinates of the center of mass. It's not necessarily the center of mass. You can consider any point. So we can consider the coordinates of the center of mass and the rotation angle. So here we have xg, yg, and theta. Knowing these 3 parameters give a full and unique description of the body position. What means unique? It means if I know these parameters, this set of 3 parameters, it corresponds only one position. If I change this set, change the values, I will obtain another unique position. So this set of 3 parameters describes in a unique way the position of the rigid body. And this is what means the degree of freedom. The degree of freedom of a body or a link is the number of independent parameters that are required or needed to describe the motion, the body's position in a unique way. So here in 3D, in 2D, I need 3 parameters to describe the body's position. So the degree of freedom of a rigid body in plane, it is a 3. Why? Because I need 3 parameters to describe the motion. And these 3 parameters actually correspond to the elementary motions. So here, for example, the 2 coordinates of the center of mass describes the translation motion, the 2 elementary translations of the rigid body. The theta, the rotation angle, describes the rotation or the elementary rotation of the rigid body. So for a rigid body, I need 3 parameters to describe in a unique way, to define in a unique way the position. That means that this rigid body has 3 degrees of freedom. Okay? Now, in space, just to give an overview rapidly, we are not going to focus on 3-dimensional problems. Now, in 3D, a body has 6 degrees of freedom. Why? Because I need 6 parameters to describe the motion. The 3 coordinates of the center of mass and the 3 angles of rotation. And this corresponds to 6 elementary motion of the body, 3 translation along the 3 axes, and 3 rotations around the 3 axes too. So in 2-dimensional kinematics, the rigid body has 3 degrees of freedom, and in 3-dimensional kinematics, a body or a link has 6 degrees of freedom. Now we move to the third part. Having now a knowledge of how many degrees of freedom has a link, one link, now let's move and see how we can calculate the degrees of freedom available in a mechanism, or how many elementary motions has a mechanism. Okay. So the mobility is the number of degrees of freedom in a mechanism. It is also like for one link. It is the how many independent parameters I need to describe the motion or the position of a mechanism. If it is one link, I need 3 parameters. So the degrees of freedom is 3. Now here, it's a trade-off, because links has some degree of freedom, but they are connected. So when we connect, we cancel some degrees of freedom. So there is a trade-off between some available degrees of freedom in links and some canceling of degrees of freedom due to connection. So we need to study that in deep. So here, so at the end we will come up with the equation of mobility, the equation that will give how we calculate mobility, and mobility will denote it as capital M. Now, here, let's consider that the mechanism is made, okay, of course, of links. Here we consider it is made of a certain number that we will denote it as L. So here we assume that we have L links, L rigid bodies in the mechanism. Now, knowing that for any link, I have 3 degrees of freedom. Okay. So in all, how many degrees of freedom are here available? For any, there is a 3. The available degrees of freedom is 3 times L. Okay. So it's a kind of stock. You like in a bank, you have your account and you stock you save your money there. So what is saved here as degrees of freedom in a mechanism is 3 times L. One link has 3 degrees of freedom. L links together have 3 times L links. So I have in all available in the mechanism 3 times L degrees of freedom. So this is okay, like in your account, you'll use only this one. You cannot take more. So if then you will see we are going to take from this one. We are going to consume these degree of freedom. So first, it is the ground. The ground is the first consumer. Now, the ground will already take how many? The 3. Why? The ground is considered is not. It's considered non-moving. It's the reference. I will study the motion of this link, this link, this link, this link, and the other one relatively to the ground, to this one. So for me, this one is not moving. When I consider the motion relatively to a reference, I'm considering that reference is fixed, is not moving, is static. So instead of having 3 degrees of freedom, okay? So now I have only available in the mechanism 3 times L minus 1. Okay. Now I removed the degrees of freedom one by one. Why? Because now the mechanism will work together. It's when I say there is a remaining 1 degree of freedom is not necessarily in one link. Okay. So the ground will consume 3. Now I have 3 times L minus 1, but I need to see this one as a whole mechanism, as a whole mechanical system. It's not necessarily available in one link and not other. Now, to make a mechanism, I need to connect the links together. And how I connect the links together? Using kinematic pairs. And kinematic pairs, how they work? They cancel again degrees of freedom. So now, let's assume I have used a certain number. Okay, here I schematize it here for kinematic pairs that allow 1 degree of freedom. Now, in general, let's assume that I have a certain number J1 of lower kinematic pairs or of kinematic pairs that allow only 1 degree of freedom. Now, each one of these, so for example, this one, if it allows 1 degree of freedom, it does mean it cancels 2. So this one has canceled 2 degrees of freedom. It blocked 2 degrees of freedom. This one has also blocked 2 degrees of freedom. This one has blocked 2 degrees of freedom. So here, okay, I have 1, 2, 3, 4, 5. 5 1 degree of freedom joints. They allow, each one allow 1 and each one block 2. So in all here, I block 10. If I have the general J1 number of lower kinematic pairs confusing low kinematic pairs and 1 degree of freedom joints because in planar motion they are the same. The 1 degree of freedom joints or lower pairs are the pin joints and prismatic joints, and the high pairs or the 2 degree of freedom joints are the cam and gear joints. So here, the J1, I will have all the pin and prismatic joints. Each one will block 2 degree of freedoms. So in all, I have consumed here 2 J1. So I have started by 3 times L. This is the available degrees of freedom in the mechanism. I have consumed 3 degrees of freedom by the ground, and I have consumed 2 times J1 degrees of freedom by the lower pairs, by the kinematic pairs that allow only 1 degree of freedom. Now, likewise, now if I will also use some of higher pairs or that allow 2 degrees of freedom, so they block 1. So this one, for example, it blocks only 1 degree of freedom, so it consumes only 1 degree of freedom. This one, it consumes 1. For this right example schematized here, I have canceled 2. But if I have in general J2 higher pairs or higher kinematic pairs, I will consume J2 degrees of freedom. So I have started by 3L. This is the available degrees of freedom in the mechanism. I have consumed 3 by the ground. I have consumed 2 times J1 by the lower pairs, and I have consumed J2 by the higher pairs. Okay? So now this is it. What is remaining is the mobility. The mobility is, okay, it's the balance between what is available, what you save it, what you put as degrees of freedom in the mechanism available in each link, and what you consume it by the ground and the different kinematic pairs. Now, it's like your fridge. You go and you save, you put your what you need in there, but at the end, you consume some of it. So the ground will consume 3 degrees of freedom. The 1 degree of freedom joints, each one consume 2. So at the end, in all, they will consume 2 J1. And the higher pairs, each one consume just 1 degree of freedom. So in all, if we have J2 higher pairs, we have consumed J2 degrees of freedom. So this is how actually a mechanism works. A mechanism is mainly what is physically present in the mechanism are links. So the links. Now the links needs to be connected. So to get this connection, they pay. It's like a trade. They pay kinematic pairs by their own degrees of freedom. What they get back is they are connected together. Now also, to build a mechanism, links need a reference. Now again, here it's a trade. They pay the ground by some degrees of freedom. What they get in return is a reference. So reference to their kinematics. So all the kinematics that will be studied will be reference to that ground. And this is how we can build a mechanism. So it is a trade of degrees of freedom. The links will pay everything they have saved. They can only save degrees of freedom, and they pay by their degree of freedom to get in return a reference and to get in return a connection. So they are connected together. So this is the mobility equation is what's also called the Grobler-Kutzbach equation. It's first established by Grobler and then modified. The one presented here is the one established established by Kutzbach. Now, the one of Grobler uses the half joints because higher pairs sometimes considered as half joints. I don't want to talk of that, so I prefer distinguishing kinematic pairs as higher and low. Now, okay, if we follow the same idea, we can also establish the equation of mobility in 3D for three-dimensional kinematics. So we start by what we links have available as okay. There is some this one is not modified, so this is it's of planar mechanisms. We need to focus on the one at the left here. So what we have saved are 6 degrees of freedom, and in all we have 6L degrees of freedom. The ground now will consume 6, and for the joints we have more types. There is some joints that allow 1, so they consume 5. There is some joints that consume allow 2, so consume 4. The joints that consume 3, so they allow 3, consume 3. The other one allow 4 and consume 2, or allow 5 and consume 1. So at the end here we have the mobility in three-dimensional for three-dimensional mechanisms is 6 times L minus 1. L is the number of links, minus 5J1 minus 5 times the number of kinematic pairs that allow only 1 degree of freedom, minus 4J2. J2 is the number of kinematic pairs that allow 2 degrees of freedom, and minus 3J3. J3 is the number of kinematic pairs that allow 3 degrees of freedom, and minus 2J4. J4 is the number of kinematic pairs that allow 4 degrees of freedom, and at the end minus J5, which is the number of kinematic pairs or joints that allow 5 degrees of freedom. Okay, this is just presented. We are not going to use it. We will focus more on planar mechanisms. Now, let's we are going to see how useful is this number. Okay, it's fine. We have a mechanism. We can count the links. We can count the kinematic pairs, and we can calculate the mobility. But what's after? What's after this number? What means this number? Okay, if at the end I will get m equal 2, what does that mean? If I have a negative number, what does that mean? So in this fourth part, we are going to try to interpret the meaning of the mobility value. Now, the mobility, if you remember, it's the difference between two things. The mobility is the difference between what is available in the links and what is consumed by the ground and the kinematic pairs. Now, if mobility is positive, it means that what is available in the mechanism are higher or more than what is consumed. So we have something available, degrees of freedom available in the mechanism, in the links, in the elements of the mechanism, and we have consumed them to connect them together, but still, so there's still some motion. So I agree with you that there is some motion. Now, if there's still some motion, so I can consider it here as a mechanism. So if M is positive, I can call the mechanical system as a mechanism. And this is what we need. This is what we need here in our course, because we are interested in mechanisms. We are interested in things that can move, because we need to transform the motion. Now, let's focus only if it is positive or negative. Now, if it is 1, 2, 3, or more, we'll discuss this one later. Now, if the mobility is 0, now, if the mobility is 0, it means that the ground and the kinematic pairs have together consumed all the degrees of freedom available in links. Now, it means there is no motion possible. It's static relatively to the ground. Don't forget that the ground itself is a reference. It's not necessarily static. Now, it will make as if mobility is 0, there will be as a whole rigid body. It's called a structure, but as if it is a whole rigid body. Why? Because no link can move relatively to the ground. So no link can move relatively to other one. So everything is fixed, everything is static with respect to the reference, which is the ground. Now, if the ground is also fixed, so in that case, everything is fixed, static. Now, if the ground, the link that is considered as the ground or a reference, move, everything will move with it as a whole rigid body. Now, but what if M is negative? Now, if M is negative, it's like you consume more than what you have. Now, here starts to be a problem. Now, it's sometimes useful. You can take a credit from your bank. You need more than what you save it, but it's sometimes useful. Okay, sometimes useful also in mechanic, and this is called preloaded structure. Why it is preloaded? Because now here we need more than the available degrees of freedom. We will not be able to assemble the elements together to make the structure. I will not say anymore if M equals 0, if M is negative, I will not say anymore a mechanism. It's a structure. So if M is 0, it's a structure. I can, I will consume all the degrees of freedom. I can assemble them easily. Now, if M is negative, it's not easy at all to assemble the structure. So I need to have some forces. I need to deform some elements to assemble or to connect the elements. I will not say links here. To connect the elements together. So here, if it is negative, it is a preloaded structure. I need to deform some elements to be able to connect the elements together. You cannot have your bodies keep their own shapes. You need to deform the shape. You need to have some distortion in the links. I'm going to show this one on some examples. Now, this is okay. Yes. Now, this one, let's consider if you have two bars and you want to connect them with two pin joints. Okay. I have two bars, so two links. Yes. So L is equal to 2. I have here two pin joints, two lower pairs. So J1 will be also 2. I don't have cams, I don't have gears, so I don't have any contact between cams or gears here. So J2 will be 0. So if I will substitute in Grobler equation, in the equation of mobility here, I will have 3 times 2 minus 1, minus 2 times 2, and minus 0. Okay? So at the end, I will come up with what? A mobility is minus 1. Okay? So if the mobility is minus 1, it's negative 1, it's negative mobility. It's loaded structure. So imagine this one. You have these two bars, and you want to connect them. One bar, okay, they're not necessarily the same length. You will not be able to connect. You will connect them only in the condition that here the the purple link is deformed. You cannot connect them while keeping that the bar has this straight shape. You need to distort, to have some distortion in this link in order to connect them. Is this clear? So if it's a structure, it might mean the structure is not moving with respect to the ground. There is no possibility of relative motion. But here we have another problem, which is that it's not easy to assemble. To assemble the system, we need to apply some loads to make some distortion in some elements. Now let's move to, I will add one bar and I will add one pin joint. Now if I will add one bar, I will have now the number of links are 3. I will have 3 pin joints. So J1 is a 3. Okay, still I'm not using cams and gears, so in all J2 it will be 0. So if I will substitute, the mobility will be 0. Okay, 3 times 3 minus 1, minus 2 times 3 minus 0. This will give 0. So there is no degree of freedom for this system. But it's quite easy to assemble them. I can find a way to assemble them without any effort, without any mechanical load. And I can assemble them while keeping the original shape of links. So here I have a structure, a simple structure. Now, this structure has a mobility 0. There is no possible motion. There is only the possibility that they can move together as a whole, one rigid body. Okay? There is no possible, the purple bar cannot move relatively to the blue one. This one, the cyan bar, cannot move with respect to this one. And now, if I fix the ground, there is no possible motion. You cannot move the other 2 bars. It's impossible. The degree of freedom is 0. So that's why, for example, in metallic structures, metallic bridges, Eiffel Tower, for example, there is a plenty of use of this triangular structure. Why? Because this one does not allow any relative motion. Okay, let's increase more. So I will add one bar and I will add one pin joint and see what happens. Now I will have, okay, forget this one. I will have 1, 2, 3, 4 bars and 4 pin joints. Okay, so I will have L equal 4, J1 equal 4, J2 equal 0. Now if I will substitute in the Grobler equation, I will have 3 times 4 minus 1, minus 2 times 4, and minus 0, and this will give me 1. 1, it means that, okay, it's fine. I can assemble easily the mechanism. Now, as it is mobility is 1, it's strictly positive. So I can talk about a mechanism. So I can assemble the mechanism together. I can assemble them together. But more than that, it's also possible to move. Even if I fix one link as the ground, consider it not moving, static, the other links can move. Now, but if the degrees of freedom is 1, it means I need just one parameter to describe the motion. So let's be back to this 4-bar mechanism. So I have 4 links connected together with 4 pin joints. We have just calculated, and the mobility is 1. Now, the mobility is 1. It means that I need one independent parameter to describe uniquely the position of the link. Now, it means if this parameter, for example, is the angle of rotation of the link 2, if I know this angle, it's fine. This is the parameter. Or also, if I know link 4, this can describe the motion of the mechanism. So if I give you the angle of theta 2, you will be able to find the position of the whole mechanism. You will be able to find the position of link 3, and you will be able to find the position of link 4. Why? Because link 3 and 4 are tightly dependent of the position of link 2. So here, it's only possible to fix one parameter. It can be here link 2, link 4, or anyone. But as soon as you fixed one position of 1 degree of freedom, not necessarily link, but okay, here for the bar it has only 1 degree of freedom. Now, if I fix 1 degree of freedom, mobility 1, if I fix 1 degree of freedom, let's say link 2 is 60 degree. Now, if it is 60 degree, now I cannot fix the other one. I need to calculate that one. They will be automatically find it. So to describe the motion of this mechanism, I need only one parameter. So if the mechanism has a mobility equal 1, I need one parameter. I need to define externally 1 degree of freedom. It means I need 1 input. So for this 4-bar mechanism, I can have only 1 input. Why? Because m equal 1. If mobility is equal to, I can have two inputs. It's not I can. I should. I have 2 inputs and only 2. If mobility is m, so you need m inputs. Now, when I say input, it's a degree of freedom. You need to control by an external source of energy 1 degree of freedom if it is 1 input, 2 degrees of freedom if it is 2 inputs, 3 degrees of freedom if it is 3 inputs. Now, if I say 2 inputs, 2 degrees of freedom, the 2 degree of freedom you can control 2 degree of freedom on the same link or on 2 different links. What tells mobility is only the number of degrees of freedom that should be controlled externally. For example, by the user, if you have a mechanism and you want to use it, you need to work with if it is m equal 1, you need to work with one input, and more, you need more inputs. Now, this is very helpful also for the designer. Now, when you design a mechanism, you need to check what is the mobility. Now, maybe you design a mechanism and you come up by a mobility equals 0 or negative. So you want to design a mechanism and you come up with a structure. Also, maybe you have only one input available, and you design something that has a mobility equal 2. It's not good. So here, for the 4-bar mechanism, mobility equal 1, it means you need to control by an external source one link. Why one link? Because here each link has only 1 degree of freedom. So for example, if I have a motor to control link 2, it's fine. The other one, 3 and 4, will automatically be driven by link 2. Their motion will be automatically controlled and defined and predictable by the motion of link 2. As soon as I assign the motion to link 2, 3 and 4 will be driven automatically. Now, I come back to the question of your colleague. Now, this is what happens if I control less than required. Now, this is a 4-bar mechanism. Okay, a 4-bar mechanism has a mobility equal 1. So I need to give one input. Now here I didn't control any one. I made just, okay, the input goes randomly. So if the input is randomly, I'm not controlling it. I can have any motion for the mechanism. The motion is unpredictable. So if you give to the mechanism less inputs than required by the mobility, the motion of the mechanism, the position of the mechanism is unpredictable. Okay? Now this one, and try to focus on the pink link. Try to focus a little bit with the pink link. Now, this case, I have given to the mechanism more inputs than required. The 4-bar mechanism has a mobility equal to 1. And here I have controlled 2 links. I have assigned the motion for the 2 cranks, for the red bar and the cyan bar, this one. Okay, so as if I have a 4-bar mechanism, and I have put a motor here to drive this crank, the red bar, and I have considered another motor to drive the second crank here. What happens now for the coupler here? It's deformed. You cannot maintain that this bar behave as a rigid body. It's stretching enormously. It's even this kind of stretching is only theoretical. If it is in reality, this will fail. So if we control more inputs than what is required by the mobility, necessarily will deform one or more links. Some links will be deformed, and this is against of the assumption of mechanism. Mechanism should consider only rigid bodies here. And okay, the deformation here can be so significant that can induce failure. So before using your mechanism, you need to be aware, or designing a mechanism, you need to be aware of its mobility. If you have a 4-bar mechanism and you work with it and you control 2 links, this is what will happen. You will break your system. You will break your mechanism. Now, the perfect case is, and this is what should be done, is you control as many inputs as the mobility. In this case, you have a very predictable motion. You can know the position at any time, and you are be safe. You will be safe as you will not have any distortion. Theoretically, you will not have any distortion in your links. So it's important for a mechanism to know its mobility in order to determine how many inputs that this mechanism can take. So you need to know how many degrees of freedom can be controlled externally and should be controlled externally. So now we are going now to have some examples. So we are going to consider some mechanisms, starting from simple ones to a little bit more complex ones, and we are going to, for each one, to establish or to find the number m, or the mobility of that mechanism. So let's start with this one. Now, this one, we have n bars, a certain number. It can be 5 bars, 10 bars, 20 bars. They are connected in series, one after the other, and they are connected with only revolute joints, pin joints, or also they are called turning joints. Okay, they allow only rotation. Now, we will need the same number. So we will need, if we have 10 bars, I will need 10 pin joints. If I have 20 bars, I will need 20 pin joints to assemble or connect all the bars together. Now, for this one, we need, okay, so it's one closed kinematic chain. It is one loop here, the assemblage. I need to find the mobility. I will have, okay, as you have said exactly, the number of links are given here. We have n bars and links. They're connected together with n revolute joints, pin joints. Pin joints are lower pairs. They allow only 1 degree of freedom. So pin joints or turning joints or revolute joints will be counted in J1s. So here J1 equal n. In J2, I have nothing. I don't have cams. I don't have gears, so there is no contact, no direct contact or line contacts. So here I don't have any cam joint or gear joint. So substituting this, I will have m equal 3 times n minus 1. N is equal is L minus 1 minus 2 times n and minus 0. Okay, and 3 times n minus 2 n, it will be n, and I will have the minus 3. So in all, I will have n minus 3 as a degree of freedom. Now let's move. Okay, to this example. Now, okay, the solution is here. This is the Watts 6-bar mechanism. Here the number of links are 6. So what we have here, so 4 binary links. So I have this bar, the first bar, the second bar, the third bar, and the fourth bar. So these are 4 links. In addition to this, I have 2 ternary links that will complete the number of links to 6. So I will have this one, it will be the fifth one, the fifth link, and the sixth link. In terms of lower pairs, I will have here 7 pin joints. 1 pin joint connecting 1 and 2. This one, the second one, will connect 2 and 5. I will have a pin that connects 5 and 6. I have a pin that connects 1 and 6. I will have a pin here that connects 4 and 6, and this pin connects 3 and 4, and the last one, this pin, which connects 5 and 3. So in all, I will have 7 pin joints or revolute joints. It is a lower pair. It allows only 1 degree of freedom. So J1 is 7. And I have no higher pair here. I have no joint that allows 2 degrees of freedom. So J2 equals 0. Now, when I will substitute the equation, I will have 3 times 6 minus 1, minus 2 times 7 minus 0, and this will give 1. So for a Watt 6-bar mechanism, the mobility is 1. So if we need, of course, to choose one, the ground, a link as the ground, and another link as the input. Now, let's have this other 6-bar mechanism. So here, I have 5 moving bars, okay? But first, I need to start and count the ground. The ground is here, and as I have said, I'm not drawing the real shape of the ground. I'm just drawing here the connections of the ground. Even though here there is multiple connection with the ground is only one body, one link. So I even here I have 3 connections with the ground. I consider this as only one link and one ground. There will be always in a mechanism only one ground. So I will start here by counting here 1, the ground. Then I will count 2, 3, 4, 5, and 6, the other moving bars. So I will have L equals 6. J1, okay, the joints that allow 1 degree of freedom are either the revolute joints or the prismatic joints. Here I will have only pin joints, the revolute joints. So if I will count them, I have here 6 pin joints. Except that I have 5 pin joints. They are ordinary of order 1. They connect only 2 links, and this I will count them each one once. So here I will have 1 pin joint between 2 and 3. Then I will have 1 pin joint between 5 and 6. I will have 1 pin joint between the ground and 6. I have 1 pin joint between 1 and 4. And the 5th one is that connects the ground with link 2. So these are the 5 pin joints of order 1. They connect only 2 links. So I consider this each one as only 1. Now I have this one, the 6th pin joint. This one connects 3, 4, and 5. It connects 3 links. So this is a joint of order 2. So I will count the pairs considering their order. So if it is a order 2, I need to count it twice. If it is order 3, I will count it 3 times, and so on. Now here, why? Because Actually, this one it's a kind of two pin joints. There is one that connects 3 to 4, and another one it connects 4 to 5. I should consider it twice. Why? Because it blocks here 4 degrees of freedom, the two translation between 3 and 4, and the two translation between 4 and 5. So that's why it is of order 2, and that's why I'm counting it twice. So I have 5 pin joints with order 1, each one are counted 1, and I have 1 pin joint of order 2, and I will count it twice. So in all, I will have 7 pin joints, 7 lower pairs. So J1 is 7, J2 is 0. Again, I don't have any higher pair. I don't have any cam contact. I don't have any cam joint. I don't have any gear contact here. So at the end, I will have a mobility of 1. Now, this is a little bit predictable that here for this kind of mechanism that I will have a mobility of 1. Why? Now, if I focus on the left part of the mechanism, the part that is built by link 1, the ground, 2, 3, and 4. This is a 4-bar mechanism. So if it is a 4-bar mechanism, we have already calculated this, and it is of mobility 1. What does that mean? Now, if I know the motion or I have input here in 2, or I know the position of 2, the positions of 3 and 4 are completely defined and in a unique way. So if I define the position of 2, I will define the position of 3 and 4. So especially the position of 4 is also defined. Just by defining the position of 2, the position of 4 is unique and predictable. Now, if I consider the right part, again, it's a 4-bar mechanism. The mobility is 1. So as the position of 4 is predictable and known and controlled using 2, now, and the mobility is 1, so again 5 and 6 will be also controlled just by 4. So moving 2 will move automatically 3 and 4, and if 4 is moved, will move automatically 5 and 6. So just by moving 2, knowing the position of 2, the positions of 3, 4, 5, and 6 are predictable. So just by having one input, I have a predictable motion for all the link. And this is just one input, predictable. It means that the mobility again is 1. So this is just to interpret and to check that our equations are giving something logical. Okay. One more example here, the slider crank. So this fourth example, the slider crank mechanism is okay. It's a kind of 4-bar mechanism. Just 1 bar is moved and changed by a slider. So if I see the number of links, we have first the ground, the second link is the crank, the third is the coupler, and the fourth is the slider. So in all, we have L equal 4. Now, these are connected by 3 pin joints. By turning joints, we have the first pin joint between the ground and the crank, another pin joint between the crank and the coupler, and the third pin joint between the coupler and the slider. Okay, so these are 3 pin joints, but they are completed by another type of lower pair, which is the prismatic joint. So the slider is translating along the ground, so there is a prismatic joint here between the slider and the ground. The prismatic joint allows only 1 degree of freedom, so it is counted with the lower pairs, it is counted with the J1s. So here we have L equal 4, J1 equal 4, no higher pair here, and if we substitute to the equation, we'll obtain mobility equal 1. Here we have 3 links. Yes, we have the cam, we have the follower, and of course, first we have the ground. So in all, we have 3 links, L equal 3. J1, here we have 1 pin joint, because the cam rotates, have a rotation motion about the ground. So there is a pin joint between the ground and the cam. And we have another lower pair, which is the follower is translating along the ground in the vertical direction. So here we have a prismatic joint. It is the second lower pair. And this will give that J1 is equal to. Now, the only here special case that, they knew that there is direct contact between the follower and the cam. The cam drives the follower by simple contact, and this is a cam joint. It is a higher pair. It allows 2 degrees of freedom. So this one is counted in J2. So L equal 3, J1 equal 2, and J2 equal 1. And if I will substitute, I will have 3 times 3 minus 1, minus 2 times 2 minus 1, and this will give 1. Okay. Here you will have 3 gears. But we need the ground. We need the ground. So the thing is the ground. So we have the ground and 3 gears. In all, I have L equal 4. Now, each of the gears is rotating or has a fixed axis rotation. So it's rotating about a fixed axis about the ground. So I have 1, 2, 3 pin joints between each gear and the ground. So J1 is a 3. Now, the higher pairs are the number of contacts between the gears. So I have here, actually, the pairs are the connections. So I have here a connection between 1 and 2, between the 2 gears, and this is one higher pair. One connection, one joint that allow 1 degree of freedom. I'm trying to, just try to, pen. Yes, I have here one connection here between the gears. And this is the first higher pair, the first gear joint. And I have a second one here. So I have 3 gears, but I have only 2 connections, gear joints. A connection between 1 and 2, and another one between 2 and 3. So J2 here is equal to, I have 2 higher pairs. So if I will substitute, I will have M times, M equal 3 times 4 minus 1, 4 links minus 1, minus 2 times the 3 pin joints, minus 2, the 2 gear connections. And I will have here a mobility equal 1, which is expectable, as for this ordinary gear train, I can have only 1 input. If I will drive this gear, which is here, the gear 2, the position of 3 and 4, the velocity of 3 and 4 is uniquely defined. I can have only 1 unique position corresponding to a given position of the first gear. We have here 1 central gear in the middle here. It's better to look at it from the other side, but it doesn't matter. Now, we have another outer ring gear here what is I have here in green. So I have the central gear, the sun, the outer ring, which is called the ring shortly. In between there, I have another gear, which is called the planet gear. This planet gear has a general motion. So the sun has a fixed axis rotation, the ring has a fixed axis rotation, but the planet has a general motion. So here there is three gears, three planets, but let's focus here on the example. I have only one planet. Now, the planet is actually, the planet gear here is held by an arm. It's hidden here in the video by this arm. So what I will have is that the arm is rotating around, let's say this is the central pin joint. Let's have it, for example, A. The sun is rotating about A. The arm in yellow here is rotating about A, and the ring is also rotating about A. Just in between, I have the planet, which is rotating about B. And AB is the arm. So B is the other extremity, the other end of the arm. J1 is 4 because I have this central pin joint, the A. It's connecting 4 links together. I have the sun or the central gear rotating the ground. I have the arm rotating about the ground. And I have the ring rotating about A, the ground. So the central pin is connecting the sun, first the ground, sun, the arm, and the ring. So this one is connecting 4 links. So it is order 3. So I should count it 3 times. It is 1 pin joint between the ground and the sun, 1 pin joint between the arm and the ground, and 1 pin joint between the ring and the ground. This pin joint is of order 3, so I should count it 3 times. And this one is of order 1. I should count it only 1 time. So I have 1, 2, 3 for the central pin joint and 4 for this one. So in all, I have J1 equal 4. So if I will substitute here, L equal 5, J1 equal 4, J2 equal 2, I will get that the mobility is 2. So here it is a good example of a real and useful mechanism with a mobility equal 2. What does this mean? I need here 2 inputs. So for example, you can control independently the sun and the arm. So the rotation of the sun and the arm can be independent of each other. So you fix the velocity independently. They can have or not the same velocity. They can have or not the same direction. So you have 2 possibilities to control the motion. Okay. The links are 7. I think you all agree. We have the ground. We have a ternary link here too. I have a cam 3, and I have 3 bars, which will be 4, 5, and 6, and I have the slider 7. So L is equal to 7. Now J1, the connections. What I will have? I have 1. Okay, I will choose a highlighter maybe. Okay, so I will have 1, 2, 3, 4, and 5 pin joints, simple pin joints of order 1. Each of these pin joints, So 5 pin joints connect each one to links. So they are of order 1. So I count them only 1. However, this pin joint, it's connecting 4, 5, and 6. So this is of order, it connects a 3, so it is 3 minus 1. It is of order 2. So this one I should count it as 2 times. So I have 5 pin joints of order 1, 1 pin joint of order 2, so I counted 2 times. I have here 7 lower pairs. Prismatic joint is number 8. So in all, I will have J1 equal 8. And for J2, I have this one, the contact between the cam and the ground. So I have J1 equal 1. I have only one simple contact, J1. J2 is equal 1. I have only one higher pair. So if I will substitute 3 times 7 minus 1 minus 2 times 8 minus 1 will be equal 1.